Energy is defined as the ability to do work. So when someone asks you, do you have very much energy today? What they're really asking is how much work could you do? Energy isn't necessarily the actual doing of work, but it's the ability to do work. So think about eating a nice big hamburger. When you eat that hamburger, all of the energy in that food, which is quantified in calories, gives you the ability to do more work. You might actually do some work or you might not. We divide energy into two big categories. The first is potential energy, which is energy that's being stored but isn't doing any work right now. So you might think of things like an apple that stores energy in the chemical bonds, that you could eat the apple and then use that energy to do some work, but the apple itself isn't doing any work. The other big category is kinetic energy. That's energy that's actually in motion, that's in the process of doing some work. So these are two big categories: potential energy, that could do some work but isn't right now, and kinetic energy, where we actually do have some motion and some work going on. We can further divide these categories. Potential energy, we can store energy in a variety of different ways. We can store it in the chemical bonds between different atoms and different molecules. We can store it by there being a gravitational field. For example, if you pick a rock up off the ground, that rock has some potential energy because now it's up high. And if you dropped it, gravity would pull it down, and that rock would then have some kinetic energy and hit the ground and do some work. We can store energy in batteries. We can store energy in the nucleus of an atom. That's nuclear energy. And we can store energy in mechanisms. Like, for example, if you took a mousetrap and set the spring would be storing some energy in it. And we call that stored mechanical energy. Gravitational potential energy is one particular kind, and it's stored in objects that are up high and could fall. So by virtue of being up high, they have some gravitational potential energy. It depends on three things: how heavy the object is, or its mass, its height above the Earth, so something that's higher up has more gravitational potential, and how strong gravity is right there. So for example, if you have a rock on the Earth and you hold it up in the air, it has some potential energy. That same rock, if you hold it up on the moon, doesn't have as much potential energy because in the moon, gravity isn't as strong. We have elastic potential energy. That's the energy that's stored by something that can stretch, like a rubber band, or compress, like a spring. So if you had to take a rubber band and stretch it and then let it go flying, when it's stretched out, it has energy that's stored as elastic potential energy. We also have chemical potential energy. For example, gasoline in your car stores energy in it. Chemical potential energy is simply the energy that's stored in chemical bonds. So things like wood has chemical energy in it that's released when you burn it. The same thing for coal. The same thing for food. So we can store energy in a variety of different ways, and there are different types of potential energy. There are also different types of kinetic energy. Remember, kinetic energy is energy in motion. So one example would be electrical current. That's actually electrons moving through a wire. Thermal energy is little particles vibrating back and forth. Sound energy is also vibrations moving through the air or a substance, some kind of medium. Electromagnetic energy is the energy of light waves, also X-rays, microwaves, radio waves, all kinds of different waves. And then we have the energy of motion of large objects, and we call this mechanical kinetic energy. So think about like the gears in a clock turning, or a person running along. This is all kinetic energy because of the motion of a large object. The kinetic energy that something has is given by this equation. Kinetic energy is 1/2 mv squared. Don't worry, you don't need to memorize it. What I want you to see, though, is that the kinetic energy depends on two things. It depends on how heavy the object is, the mass, and how fast it's moving. So if it's moving faster, it has more kinetic energy. If it's a great big thing, it also has more kinetic energy. It's worth noting that the unit of energy in the international system is the joule, and that's just abbreviated as J. So some types of kinetic energy that we mentioned. Mechanical energy. Think about the energy of the moving things or the moving parts in a system. So this picture shows something called a Rube Goldberg machine, which is a machine that has lots of complicated parts and bits moving all around. There's a lot of mechanical energy in this system. Electrical energy is the energy associated with electrical charges. And if it's stored in a battery, it's electrical potential. If it's actually flowing electricity or current electricity, then it's a kinetic version of electrical energy. Electromagnetic energy is light or radiant energy that actually has electric and magnetic fields. And one of the cool things about electromagnetic energy is that it can travel through empty space. It doesn't need a medium to travel in. Thermal energy is what you get if you took all the particles made up in an object and you were to add up all of their kinetic energy. So think of all the different ways they can move. They can go side to side, that's translational. They can rotate, they can spin, or they can vibrate in place. If you were to sort of tally up all of the energy of those individual particles, that would be the thermal energy. We think of it more commonly as heat energy. Nuclear energy is the potential energy that's stored in an atomic nucleus. And when those nuclear bonds, the things that hold the nucleus of an atom together, when those forces are released, you have a tremendous release of nuclear energy. Next, we're going to look at something called the law of conservation of energy. This one says that energy doesn't ever get created or destroyed, it just changes form. So the picture that's shown here shows a solar cell phone charger. So imagine that you have some sunlight, that's electromagnetic energy, that hits the solar cell. The solar cell turns the electromagnetic energy into current electricity. That electricity flows through the wire and into the phone's battery. In the battery, that electrical energy is converted and stored as electrical potential energy. When you turn the phone on, that stored energy is converted into light energy to light up the screen of your phone, and sound energy when you're actually talking. So notice that what happened there is the energy kept changing forms, but it never was created or destroyed. It is often the case that when energy transfers from one form to another, you end up with some energy being converted into heat because of friction. So here's just a picture that shows the transformations for our solar cell phone charger from light to electricity to electrical potential energy to sound energy. A reasonable question to ask is, who cares about this? Like, why does anybody care about energy and transformations? Well, this picture here is a simplified diagram of how electricity gets generated and sent to your house. So if you like being able to plug in light bulbs, or you like being able to charge your cell phone, then you should care about this. So the big idea of the way a power plant works is that first we start off on the left-hand side by burning some fuel. Maybe that's coal, maybe it's a nuclear reaction, maybe, who knows. We start off somehow burning some fuel. And we use that fuel to boil some water. And when water boils, it makes steam. And that steam travels through a pipe and turns a turbine. So a turbine is, think of it kind of like a water wheel, only instead of water pouring over it, it's steam pouring over it. That steam going through the turbine causes it to turn. And that turning motion moves some magnets through some coils of wire. And when you move a magnet through a coil of wire, you actually are generating electricity. And that electricity then is sent out to power your light bulb. So you can see you have a lot of different energy transformations that are necessary for you to be able to plug things in and have them work. So some examples of transformations of energy. A light bulb is a device that takes electrical energy and transforms it into light energy. So you can see. So we start with electrical and transform it into light. And while this happens, the light bulb also gets warm. We mentioned before that when there's energy conversions from one form to another, oftentimes energy is transformed into thermal energy. So the light bulb gets hot. The engine in a car, the job of the engine in a car is to transform the chemical potential energy that's stored in gasoline into kinetic energy of a moving car or bus. And there's a lot of energy conversions that happen in this process. So the first one, in a car, we inject some gasoline into a chamber, and then a spark plug fires. And that spark plug ignites the gasoline, which releases the chemical energy that's stored in the bonds of the gasoline. That causes a chemical reaction that gives off a lot of heat. That heat causes the hot gases to expand. That expansion pushes down on the piston, which turns a crank, which ultimately results in the turning of the wheels in your car. So your car is basically just a vehicle for converting stored chemical potential energy in gasoline into kinetic energy. Sometimes there are energy transformations that aren't quite as easy to spot because they don't have, sort of bright light, loud sounds, and bangs like that. So for example, every time that you see a green plant, what plants do is they convert electromagnetic energy in the sun into stored chemical bonds within the plant. So you may have learned about photosynthesis in previous science classes. Photosynthesis is simply using light to synthesize or make chemical bonds that store energy. Another example of something that has some kinetic energy being transformed is falling objects. So think about an apple up on top of a tree. It has gravitational potential energy because it's up high. If that apple were to break off and the apple falls, what happens is the potential energy of the apple being up high gets transformed into kinetic energy as the apple comes falling down. As it falls, it loses its height, so it has less and less gravitational potential energy, but it's going faster and faster, so it has more and more kinetic energy. This is an example of seeing how energy is conserved. It's transformed from potential up high to kinetic, moving fast. But none of the energy is lost or destroyed. Another type of energy that an apple has is some chemical potential stored in the middle of it. Another example of energy transformations is anytime we have we have an object being thrown or flying through the air. So if you hit a baseball or you throw a football, when it leaves the ground, when it leaves your hand, or when the ball leaves your bat, it has high kinetic energy. It's moving very fast because you just hit it or threw it. But its gravitational potential energy is low because it's down low to the ground. As it reaches the top of its arc, its kinetic energy actually gets lower. It slows down as it reaches the top of its arc. But now it's way up high, so it has really high gravitational potential energy. On its way back down, that high gravitational potential energy is converted back into kinetic energy. As it falls down closer towards the ground, it has less potential energy, but more kinetic energy. So what you're going to work on next is taking this information about types of energy and organizing it in a graphical format.